For this problem, we are given a triangular wooden beam with a 150 mm base and 300 mm height, which carries two concentrated loads of 15 kN applied at middle third points. If the simple span of the beam is 6 meters, we are tasked to compute the bending stress of the beam. So here is our figure based on the description of the problem. And in order to solve the bending stress of the beam, we need to locate the point where the maximum moment occurs. And to do that, let us first solve for the reaction at the supports. Let's call this reaction A, and this one is reaction B. Now we can take summation moment at point A equal to 0, taking counterclockwise to be positive. We have a 15 kilonewton force that would induce a clockwise moment, so it's negative, times the moment arm distance of 2 meters, minus another 15 kilonewton force multiplied by the moment arm distance of 4 meters, plus the reaction at B times a moment arm distance of 6 meters, all equal to 0. So we can solve for the reaction at point B. We have negative 15 times 2 minus 15 times 4 plus the reaction at B times 6 equal to 0. Keep solving, we get RB equal to 15 kilonewtons. And to solve for the reaction at A, we take summation force vertical equal to 0. We have negative 15 kilonewtons plus minus another 15 kilonewtons plus the reaction at A plus the reaction at B equal to 0. So we have negative 15 minus negative 15 plus the reaction at A plus 15 kilonewtons equal to 0. We get the reaction at A equal to 15 kilonewtons. Or you can notice this by symmetry. Now that we have our reactions at the support, we can now proceed solving for the maximum moment by constructing a shear and moment diagram. So starting at the shear diagram, it's just a unit of kilonewtons. We have an upward load going from this point, let's call this point A. It goes upward with a value of 15 kilonewtons. And since there's no changes of the load between this segment AB, therefore we can construct a horizontal line going from here to there. And then we have a 15 kilonewton force going downwards, so we subtract 15 by a downward force of 15 kilonewton. This goes back to 0. And no changes between the load in segment BC, so this remains constant. And going from C, we have a downward force of 15 kilonewton, so this goes down to a value of negative 15 kilonewtons. There are no changes between the load from C to D. This is a horizontal line, and it goes up to a value of 15 kilonewtons. And this is for our shear diagram. For the moment diagram, we need to solve for the area of this shear and the length between each segment, that is 2 meters. So to calculate for the moment, that is just the area of the shear diagram. So 15 times 2 meters, that is equal to 30 kilonewton meters. Going from 0th degree, this goes in a linear fashion of first degree, increasing upward. Then it stops to a point equal to this area shaded here, that is 15 times 2, 30 kilonewton meters. And then no changes of the shear, moment from point B to point C. Since the shear here is 0, so this goes in a horizontal line. Let's move this downwards. And then from this point here, it decreases to a value of this area, 15 times 2, that's 30. So it goes back from 2, 0. So based on the moment diagram, the maximum moment is 30 kilonewton meters. Now when solved for the problem that is asking for the bending stress of the beam, that is equal to moment times the distance from the neutral axis of the section divided by the moment of inertia. We have a moment equal to 30 kilonewton meters. And we convert this into Newton millimeters to make our dimensions consistent. So we multiply this by a conversion factor of 1000 millimeters per 1 meter. Let me erase this. Times a conversion factor of 1000 Newton per 1 kilonewtons. And the distance, the highest distance going from the neutral axis of this triangle, its center is located 1/3 from the base. It is equal to 100 millimeters. And from the top, this is equal to 200 millimeters. So we select the largest value to get the maximum stress. This is 200 millimeters. Divided by the moment of inertia for a triangle. This is given by the expression I equals bh cubed divided by 36. We have a base of 150 millimeters and a height of 300 millimeters raised to the third power divided by 12. 36. Since this is a triangle. So we have 30 times 1000 over 1 times 1000 over 1 multiplied by 200 millimeters all over 150 times 300 cubed divided by 36. We get our stress equal to 53.33 megapascals. And that is the maximum bending stress felt by this beam with a triangular section. And that is our final answer.